Hi guys, welcome to GTN ABAQUS Learning.
In the last session, we looked into a propped cantilever beam with a spring attached to one of its ends. We derived the forces and displacements using stiffness matrices. We modeled this in ABAQUS and obtained similar results. We also used beam bending equations to obtain bending moment at a certain location of the beam. Now today, we will be looking into frame. First of all, we have to look into a frame element. So let's say we have a frame element like this, which has two nodes here and here. Let this be node 1, this one be 2. In this case, we will also be considering the axial direction in which the axial forces and axial displacements occurs. So here we will be considering 3 degrees of freedom. So our first degree of freedom will be in this direction, second will be in this direction, the third one will be rotation about this axis here, like this. So for this case also we'll have this one, and rotation about this axis here. Let us use our general convention, which is anti-clockwise positive. Let's say that this is our global reference axis, that's y, that's x. Now this is global system. So here we can name this one as uy1 and corresponding force be F1. We also can consider this to be, and let the rotation be UR1 and the bending moment be FR1. Similarly, we can label the displacements and forces in these axes as well. Now we will also be considering the axial direction as well. We can have axial force or axial displacement acting along this direction and along this direction. Now for this, we may want to rotate this global axis by an angle. Let's say this angle is alpha, by an angle alpha, so that new x-axis aligns parallel to the frame element. Let's say we have a new axis here, which is x dash, y dash. This will remain the same because this will rotate about the same axis, and let this be angle alpha. Then here what we'll have is this will be x dash direction, this will be y dash direction, and that will be rotational direction. Along x dash you can write u1 f1. This can also be termed as local axis because this can be assigned to different independent elements, whereas we will have one global system where all the components of the local system are summed up. We'll see that later on in the example that we're going to do today. For this case, this is our local axis for this particular element. So we can label this one as u1 f1, and this one can be u2 f2, and this rotation can be u3 f3. Similarly, u6 f6. Now we have 6 degrees of freedom. For a generalized case like this, when an element is inclined to the horizontal by an angle alpha, we can have one stiffness matrix for the element. This stiffness matrix will be 6 by 6 matrix because we have 6 degrees of freedom. So these are our degrees of freedoms. Even if you look into your lecture notes or books, you can easily find this matrix being formulated there. Here, I'll just give you an overview that if you look into our first degree of freedom, which is the axial direction, it will function as a rod. So we can consider 1 and 4 as degrees of freedom similar to a rod. In one of our previous lectures, we did look into the stiffness matrix of an inclined rod, which was a 2 by 2 matrix. We can just write the same values here. A E by L. Now, because it's axial, this won't have any effect in the second or third degree of freedom, so you can just write 0, 0. But in the fourth one, we'll have a negative value here equal to this one. This will not affect these two values as well. So here also, since this matrix should be symmetric, we can just write 0, 0, and for the fourth one, we'll get minus A E by L. Fifth one, 0, and then we'll have 0 for the sixth one as well. So here also we can just write 0, 0, A E by L, 0, 0. This one can be 0, 0 as well. What we did here is we just dropped in the values of the 2 by 2 stiffness matrix corresponding to their degrees of freedom. Now for the beam, just drop in the values of the stiffness matrix of the beam corresponding to the degrees of freedom. Eventually you'll get a matrix like this. So what we did here is we just combined the stiffness matrices for rod and beam here. Now the problem here is that since these values are derived based on the local reference axis, we have to find their corresponding values or their components in the global system so that we can add the values up for different elements. For example, let's say we have an element like this, an element like this, and an element like this. So let's say we have a structure like this. Let's say this element 1 has angle alpha, element 2 has angle beta, and this one has angle gamma here. If we look at the local reference axis, then these elements will have different local axes. Therefore, it is not possible to add them up, to sum them up to find the net forces or net displacements. We have to resolve these values into global system so we can add them up. The global system is same for every element. To find the corresponding values in the global system, we can look into your lecture notes and you'll find that if you term this as K local, KL matrix, then your KG matrix, which is the global matrix, will be equal to transpose of transformation matrix into local matrix times transformation matrix T. The way to find the transformation matrix is that when you look in this figure, we have to find what will be our local deformations in each degree of freedom as resultants or as summation of the components of the displacements and forces in the local axis. For example, let's take degree of freedom 1 here, where we have our displacement value as u1. Now this u1 would be equal to ux1 cos alpha plus uy1 sin alpha. That's our local displacement at the first degree of freedom. Similarly, you can find u2 as well, which is equal to minus ux1 sin alpha plus uy1 cos alpha. Our u3 will be equal to ur1. Similarly, for u4, it will be equal to this, where ux1 and uy1 will be equal to ux2 and uy2, and similarly for u5 as well, it will be similar to this one, but we'll have ux2 and uy2, and our u6 will be equal to ur2. We can write this equation into one matrix form. That matrix will look something like this. Now when you open this matrix, you'll find that u1 will be equal to ux1 cos alpha plus uy1 sin alpha, and all these terms will be 0. Now this is our local vector, which can be equal to T. This T is known as a transformation matrix, and we have our global vector. Generally, a variable is assigned to these trigonometric ratios where L equals to cos alpha and M equals to sin alpha. So this will be our transformation matrix here. You can just put that transformation matrix here and obtain the global matrix for each element. This one is like per element I. For the whole system, then your global will be equal to summation of all these local global matrices according to their degrees of freedoms. You can look into your lecture notes to see how this equation is derived. I have just shown here how the transformation matrix is obtained. We'll use this formulation to solve a frame which has one inclined column. So let's go into that problem. Let's say we have a frame that looks like this, and let this be alpha, which equals to 45 degrees. We can assume this beam to have a UDL of omega, which equals to equals to 1000 pounds per feet. The reason why I'm doing some problems in metric systems and some problems in US customary system is that I want to show that ABAQUS is a generalized program where the response depends upon the units that you specify. If you make an error in specifying certain units, then you will obtain wrong results, or you obtain some results that are not in standard units. Therefore, we need to be very careful assigning the units in ABAQUS. You can have this length as 30 root 2 feet and this one as 40 feet. We are given elastic modulus as 3 into 10 to the power 7 psi pounds per square inch, area as 100 inch square, and moment of inertia for both of these elements as 1000 inch to the power 4. Now we have to solve this frame given these geometrical properties, boundary conditions, and loading scenarios. Now for this case, we'll follow this similar procedure as we learned here. Now what we'll do is we'll assign this as element 1 and this one as element 2. Let's label these end nodes as 1, 2, and 3. So here you can see that each degree of freedom is locked, and similarly at 3 all the degrees of freedoms are locked. So the only degree of freedom that is available for this frame to accommodate the deformation caused by the forces will be at 2. So at 2 we have all the 3 degrees of freedoms free, which means that the node 2 can move in this direction, can move up, and can rotate as well. Now the problem here is that as this is inclined to the horizontal axis by 45 degrees, we have to assign a local axis and find the local stiffness for that local axis for this element. For 2, since this is horizontal, making an angle 0 with the global x-axis, we wouldn't have to form the local axis because this global axis will act as local axis for this system, because our x-axis here is aligned with the axial direction of element number 2. Our matrix will be 6 by 6 matrix for each element, but here we know that only at node 2 it is free to move. Therefore, we'll directly form a 3 by 3 matrix here. Now let's say 2x, this is direction 2y, and this is theta 2, which are the local displacements and rotations occurring at node 2 for element 1. We can just write our stiffness matrix considering only these 3 degrees of freedoms. So for this case, we are looking at these values here. So you can just copy these values right here, and you'll have your local stiffness matrix. Now for the transformation matrix for element 1, let's say this is T1, this will be equal to this value here, where alpha equals to 45 degrees. Now you can substitute alpha in this matrix and then write your transformation matrix here. So this will come here, and then we'll form our global matrix for element 1 as transpose K local, that's 1 times transpose matrix here. So when you do this, we'll obtain your global stiffness matrix for element 1. Similarly, you can also obtain your global matrix for 2 as, and then for the whole system we just add these two up and form our global matrix for the frame system, which will be a 3 by 3 matrix. The reason I condensed this into a 3 by 3 matrix because it is generally easier to solve for the displacements. Now for the forces, you can just look at element number 2 here. Now this is omega. Now since we are looking at forces rather than reactions, the forces will be acting downwards here and acting like this. Now this will be equal to omega L by 2. This is omega L by 2. This is omega L square by 12. This is also omega L square by 12. Now you can substitute these values here and obtain your force vector. Here this is in direction of F2y. This is in direction of F2. This is F3y, and this is F3. This is node 2. This is node 3. To write this force vector, we can write like this. F2 and F3 are moments. You can write M2 if you like. M3 for this one. Now if you substitute the values, you will get your forces. Now good thing about this is that we have our global matrix here, which is based on our global reference axis, which is this one here. Now the forces here are also based on the same. This means that we can equate it. This means it will be kg times global u vector. Now we can solve for this one because we know this and we also know this. Now what I'll do here is I'll use Excel to solve this. Let's begin the procedure here. So let us write what we are given for element 1. Alpha equals to 45 degrees. Now we have to find the sine and cos component. So just add L and M. L equals to cos radians of 45. This will be sine radians of 45. Now these are our sine and cos components. Now let us write our local stiffness matrix for element 1, small k1. Now this is our general local matrix. So for this one, we'll be looking into this matrix here. Now this one is equal to AE by L. So this will be A E by L, L1. This one is 0, this one is 0, this one is 0, 0, this one is 12 into E times I by L1 Q. This equals to minus 6 by L square. This equals to this, and this one is 4 into E into I by L. Now this is our local matrix. Let's form transformation matrix. So T, it will be cos alpha that equals to L M. For this case, we'll be looking into these 3 by 3 matrix here. That's cos, that's sine. This will be 0, so minus sine, cos to cos, cos 0, 0, 0, and 1. Now this is our transformation matrix. We can form our global matrix for this element kg1, which will be equal to multiplication of matrix and then transpose of this matrix, which is T to the power T times of K1, this local matrix, and then times with T. When you do this, you will have your global matrix here. Now what you can do is you can divide this by 1000, so to obtain value in kips. There you go. Now this is our global matrix for that element. Now for element number 2 here, copy all of this, just paste it here. Now write here L2, which equals to 480 inches. We'll change this to element 2, make this one 0, this one K2, this is KG2. Since I've logged this, it is just looking at these values here. So what I'll do is I'll just change this to here. We have assigned alpha as 0, which gives a unit matrix here, identity transformation matrix here, which means that the global reference axis is same as the local reference axis for element 2, and then we obtain our global matrix for element number 2. Now to find the global matrix for the whole system Kg, we have to add these two values up. So let's add them up, this plus this. Now this is our global stiffness matrix, and this is particularly for these degrees of freedoms. Now our force vector will look something like this. So let's make our force vector, which is F. Now here we'll have F2y, F2, F3y, F3. And our omega is 1000 per feet. So we can divide this by 12 to find pounds per inch. And we have length here, which equals to 480 inches. Therefore our F2y will be equal to omega into L by 2. Now this is acting downwards, so minus omega squared by 2. Yep. F2, which is the rotation there, we can write here minus omega into L square by 12. This will be equal to this one, and this will be equal to minus of this one. Now I can just divide this by 1000 to obtain in kips. Now we are focusing in degree of freedom 2x. Now there is no force acting in 2x, so we have 2y and 2, 2y and 2. So our force vector for this degree of freedom will be 0 in 2x direction, and then in 2y we'll have this, and in 2 we'll have this. This is kips inch. Okay, and this will be our global force vector here. Now we have to solve it to obtain our displacements. That will be u2x, u2y, and u2. Now this will be equal to m multiplication of matrices inverse of this matrix, comma this matrix here. Let's see. There we go. Did I do a mistake here? Oh, sorry, this is omega L by 2. Now let me confirm here. Let's check it at this point. What happened here? All right. Now since I directly copied this to this, for our second element here, we are looking at 3, but we should be looking at node 2. So for that case, we should be focusing in here. Therefore, we have to change this one to positive. Yep. All right. Now we have our solution. This is inches, inches, and radians. To obtain our forces, what we can do is we have our local stiffness matrix, which is this one. Now let's just copy this thing down. Now these displacements are occurring in the global axis. To find your forces which are acting at the ends of element 1 here locally, we have to change this solution into local displacements, because this stiffness matrix here is based on the local axis. To equate this and this, we have to find the components in the local axis of element 1. To do that, we have our transformation matrix. Local displacements for element 1 at node 2, which is small u1, which will be equal to multiplication of transformation matrix into your solution. Now this is inches, inches, and radians. By local, what I mean is we have found the displacements corresponding to this axis, and theta 2. Now we have to find our forces. To find our forces, what we have to do is we have to consider this whole matrix, whole local matrix, rather than only this matrix here, because now we are looking at solving forces at node 1. Now this one only considers node 2. Since we are concerned about node 1 now, we have to form this matrix. So this matrix will be easy to form. We can just copy this, write it here. And now we just have to write the proper signs for them. So this all are positive here. So we can just write minus of that, minus of that. We have our local stiffness matrix for element 1. Now to find forces, what we do is we can just copy these values right here, special only values, and then all these three will be 0, 0, 0, because these are corresponding to displacements at 1x, 1y, and 1, which are all fixed. You can just multiply this matrix with this one to obtain our solution. What we have here is in pounds, so you can just divide this by 1000. I'll just divide it here. This one divided by 1000. these are our forces which are acting at node 1 and node 2. We have to follow the similar procedure for element number 2. So for this one, we'll also form our matrix, which will be a 6 by 6 matrix. So we'll just copy this down here. I'll rename this one 3y and 3, because in element 2 we are focusing on node 2 and node 3. Here node 2 and node 3. So for this part we will have a different matrix. Let's go to our 3 by 3 matrix for element 2. Just copy this, and this will correspond to this one right here. So just paste it. Since this matrix is based on global system, we will have our displacements as these values here that we obtained. We'll just put these values here, so equal to this one. So this 3, and then these will be 0, 0 and 0. Now let's obtain our forces. Copy all of this and then paste it here. They both are local forces. Now to obtain the global forces, we all know that the local forces will be obtained as components of the global forces. Therefore, to obtain the global forces, what we have to do is we have to get the transformation matrix for this one, which is this. Now this is a 3 by 3 transformation matrix. We have to form a 6 by 6 transformation matrix. It is easy to make it, so just copy this. Just copy this right here. You can just put the values here, and I'll just copy this here, here. Now these values have to be filled with 0. So for this you can select all of it, go to find and select, go to special, blanks, OK, put 0 and press Ctrl Enter. Now these all values are assigned 0. Now to obtain the global forces, we have to multiply the inverse of this transformation matrix with the local forces. There you go. Now these will be our global forces. Global in the sense that they are obtained in the direction of the global reference axis. Now for this part as well, global forces, since the local axis system is equivalent to global axis system for element 2, these forces will be equal, so you can just make it equal. However, we do have reactions occurring at these two nodes. This will be actually F2. At these points, at nodes 2 and 3, we will have reaction forces due to this load. So the reaction forces here will be equal to this. Now just copy this, just paste it here, just the values. So here we have our reactions. Now these reactions in the x direction, which is the axial direction, will have 0. Here we have 20 acting upwards, and then 1600, 0, 20 again, and then minus 1600. Now we'll find our total global forces. Now this will be equal to this plus this. Now what we'll do here is we'll combine these two global forces to find the net forces. So our final net forces will be, if you copy this and copy this one, so for this, for the first three values, this will be equal to these values here. Now for this one, it will be a summation of this and this. So if you add these two values up, it should be equal to 0. Yes, see, these three are 0 because we don't have any reactions occurring there, so it should be 0. That's okay. And for the F3, it will be equal to these values here. Now these are our reaction forces. So now if we draw this, let's say that this is our initial shape. Now we see that these are all occurring in the global direction. This point here will move in the positive x direction by 0.003x, so it will go somewhere here, and then it will move v2y, which is negative, which means that it will move downwards a bit, and rotation here is negative, which means that it will rotate like this. So if we draw our final figure, it may look something like, where this is u2x, this is u2y, and when you make a horizontal line here, this is our radians. So if you draw a figure like this, you can get our radians like this. So this is our u2. Final configuration may look something like this. Let's plot our reaction forces here. Now let's model this in ABAQUS and see what we get. Go to part, 2D, wire. You can make this 2000. This one will be 30. This one will be 30. Now there is one option here, add constraint. So you click on this one. This will allow us to choose different constraints. So if you want two lines to have equal lengths, you just click on equal lengths and select these two lines and say done. Or if you want two circles to have equal radius, click on equal radius. Or if you want the lines to be parallel, click parallels, so it is easier to dimension them. So for this case, we have made these two values equal. This must be equal to 30 feet. 30 feet means it's 360 inches. Now you can just connect these two, and this should be around 509. So that's okay. Enter. Now you can just erase these two lines. For our horizontal one, you can just create a line here, dimension it. This should be equal to 40 feet. 40 means 480 inches. So done. Now we have it. Now let's go to materials. I'll just name this one steel. Now for this one, go to elastic. Now we are given here that our modulus of elasticity is 30 into 10 to the power 6 psi. As I have mentioned before, that you have to be consistent with your units to obtain desired results in desired format or in desired units. For example, I have a snip of a table from ABAQUS manual. If you want to draw in SI units, you can either use meter or millimeters. Now if you want your stresses to be in MPa, then it recommends us to dimension our drawings in millimeters, newtons, and mass in tons, density in ton millimeter cube. Now if you are following the US units, if you want to find stresses in pounds per square inch, then we have to use inches and pounds for our forces. So in this case we are using inches. So we can directly use PSI for the stress units. So we'll use 30 into 10 to the power 6 here. 6. Let it be 0.3. Okay, let's create our profiles. It will be a rectangular section. Now here we are given our area and moment of inertia. Now we have to find a section that matches these values. So for this one, we can just go to Excel and let us iterate it. That's A, that's the width, that's the height. Let's say this is 10, this is 10 in inches. Now area will be A times B, and our moment of inertia would be BD cubed by 12, which means it is equal to area into B square by 12. So area will be this one. This is inch 4, this is inch square. Let's solve our moment of inertia. So for this one, we can just go to data, solver. So this is our objective cell, this one, value of 1000 by changing variable B. Let's change B. Let's see what we get. Okay, so we get A as 10, B as 10.6, area as 106, which is close to 100, and moment of inertia as 1000. So let us just use this one as an approximation to the given values. A is 10, this is 10.62. Okay, now let's create our section. Section 1, go to beam, select beam, profile 1. There is our beam profile with the given dimensions. This is 0.3. Say OK. Now let us assign this section to our part. Section assignments. Select all of it. Done. OK. Now we have to assign beam orientation. Select all of it. Done. Enter. OK. And we can assign our material orientation. OK. Now after this, let's go to assembly. Let's bring our part here, part 1. Okay, I'll move this one right at the center. Okay, let's create our step. Our analysis is static journal, 1 second. We can make it high as possible, 001. Let's make it low as possible. Okay, the field output request. This is all right. Okay, let's make our boundary conditions. You can just click on Incaster, continue, this one and this one. While selecting both of them, please press Shift and then click. If you want to deselect them, press Ctrl and then click. If I want to deselect this one, I'll just press Ctrl and then click. Let's select this and this, press Shift, done, and then just Incaster them. So these are all fixed. Now let's go to load. Here we are applying line load. Click on line load, continue, select element 2, done. Now we're applying a downward UDL. Now this UDL should be in pounds per inches, so that equals to 83.33 for this case. So done. This is applying it upwards, but our load is applied downwards, so let's put this one as minus. Okay, and now we have to mesh it. So go to mesh, part 1. You can just seed it. It's 51. It's all right. Apply. Okay, so mesh it, yes, and then go to assembly. Now here you have it, we have our model here. You can save your model. Let's create our job. This is tutorial 6, frame 10. Continue. Okay, now you can submit it. Okay, all done. Dismiss. Let's see our results. Go to results, select our database, which is this one. Let's look at a deformed shape. So let's see our sketch. So where is our sketch? Here. Looks similar. Okay. So if I copy this, you can copy your window, press Ctrl C, and then you can paste it here, Ctrl V. ABAQUS allows us to copy the visual window that you see there. So you can just paste it here. Looks almost similar. Yep. Let's look at our displacements in X direction. This one. Okay. Now we can either see our values, click here, labels, apply. Now you can see different values here. Now what you can do here is go to tools query, prop values, go to nodes, and then you can select on a node you want to see the values of. So it's this one here, right? Yep. So if you click on this one, this is the solution that we are getting, 0.003 inches. Now let's look at a solution, 0.0033 inches, which is very close. Let's look at our vertical displacements. Let's select this value here. So this is still U1. Yes, okay. Query prop values. This is still showing U1. So let's look at this one. Let's look at U2. Let's go to query again. Prop values. Now it's showing U2. Okay, let's click on this one. That is minus 0.009092. So here we also obtained 0.00974, which is close. We might have some differences here because our section is not completely geometrically as equal to that of the given problem. We're just assuming an approximate dimension. Let's look at our rotation. So click on UR3. You can click here. Now this is giving us minus 0.0032 radians. Let's look at our solution, 0.003, which is very close. Reaction forces. Okay, we can see our direction. Yes. Forces. Okay, vertical. This is 17.4 occurring in F1Y. So F1Y is 17.4. Yes, that is similar. And this one is 22.6 kips. This is around 22.3, which is very close. And then we can check our reaction forces in X direction. That's a 20.6. Let's see what I have obtained here. This is 20.6 and this is also 20.6. That's okay. And then let's see our moments. RM3. Yes, okay, let's select this one. So let's go to prop values and then click on RM3. Okay, here. This is 377. And let's click on this one. That's around 1994. So let's look at our solution. 381 and 1995. That is very similar. So this is our solution, and the reactions and displacements tend to match out which means our modeling is correct, and this is generally how we verify our models. As you can see, it is easier to obtain our reaction forces and displacements, but it is kind of difficult to obtain bending moments, because for that we have to get stresses, and then we have to use the beam bending equation for that, or you can use your reaction forces and solve for them. So this is it for today. So in the next sessions we'll be looking into 2D elements. Thank you for watching till the end. Please share, comment and subscribe to this channel. Thank you.